A wave is a disturbance that propagates from one place to another. And no matter whether they're electromagnetic waves, or water waves, or any other kind of waves, all waves have certain properties in common. For example, a wave's frequency times its wavelength equals its speed. But mechanical waves can be longitudinal or transverse. While electromagnetic waves are always transverse, and in empty space, they always travel at the speed of light. But although they always have the same speed, they can have vastly different frequencies and wavelengths. And in doing so, these waves go so far as to create the entire electromagnetic spectrum. As a matter of fact, only when electromagnetic waves have a wavelength in the narrow range from 4 to 700 nanometers are the waves visible light. That is the spectrum from red to violet. Even shorter wavelengths, called ultraviolet light, are radiated by the sun. Though these invisible rays are dangerous to living things, they're absorbed and rendered harmless by the ozone in the Earth's atmosphere. Shorter still are X-rays, with wavelengths the size of atoms. And finally, gamma rays, with the shortest wavelengths of all. Gamma rays, with wavelengths as tiny as the atomic nucleus itself, are created by nuclear reactions. Longer wavelengths, extending to visible light and beyond, can be created or absorbed when atoms change from one energy state to another. Beyond visible light, there's infrared. With wavelength longer than red light, infrared radiation can be detected only by the heat it deposits. The universe is suffused with long wavelength radiation, seen as the cooled remnants of the Big Bang that started it all. That includes not only infrared radiation, but also microwaves. Microwaves are the first part of the spectrum, whose frequency is low enough to be generated by human-made, alternating current electronic circuits. The universe is likewise full of radio waves. Centimeters, meters, or even kilometers in length, radio waves complete the electromagnetic spectrum. Of course, the great Michael Faraday didn't live to see the electromagnetic spectrum. Nevertheless, it began to take shape when, envisioning electric charges surrounded by lines of force, Michael Faraday asked himself a question. What happens when these lines are set into vibration? Faraday didn't quite see the whole answer, but he wouldn't have been surprised by the picture that emerged. An oscillating electric charge creates waves that propagate along the lines of force at the speed of light. These ripples are transverse waves in the electric field, propagating in wave fronts that become flatter and flatter farther from the source, coming more and more to resemble the plane parallel wave fronts that are called plane waves. As the wave fronts pass through each point in space, the electric field vector oscillates up and down, marking the passage of peaks and valleys of the propagating wave. Thus, an oscillating electric charge is indeed the source of outward spreading ripples in the electromagnetic field. It took James Clerk Maxwell's theory to explain the nature of light and to project the image of the electromagnetic spectrum as a whole. But for all his amazing insights, Maxwell wasn't the first to see light as a wave.